Alright, so as you know, induction proofs that involve series are the most common types in the induction proof topic. We're going to go through 3 exercises in this video, and hopefully this will give you a better understanding of the process on how to solve it. We're going to talk about the 5 steps that we need to go through in order to solve any type of induction proof, and we're going to do that aiming induction proofs. None of these exercises is trivial. They all have some level of difficulty, so let's call it medium level. But this should give you a full comprehension and test your skills. So let's do it. All right, so on the first exercise, we need to prove by mathematical induction that 1 plus 2 times half plus 3 times half squared plus n half to the n minus 1 is equal to this for all positive integers. We can see right here that our base case will involve calculating p of 1. But before we get to it, we need to state the propositional function, which is the first step, writing p of n. So in this step, we're pretty much copying what the exercise has given us and stating that this is our p of n. Second step, which does involve some easy marks still. So the first 3 steps, these are the easy marks. We need to calculate the base case. We need to find what p of 1 is on the left and on the right hand side. So the base case, which is p of 1, on the left hand side is composed of the first term that shows up over here. Therefore, the left hand side is equal to 1. Now on the right hand side, we need to replace n by 1. So we have 4 minus 1 plus 2 over 2 to the 1 minus 1, which is the same as 4 minus 3, which is equal to 1. Given that the left-hand side and the right-hand side, they're the same, so they're equal, the base case holds. Now let's tackle the third step, which are also easy marks. So number 3, we're going to write the inductive hypothesis, which is p of k. And to write the inductive hypothesis, we are again copying this expression, however, substituting our n's by k's. So that's what we're going to do right now. And to finish this step, you need to write the following sentence. Assume that this is true for some positive integer k. And there we go. We have our first 3 steps, the easiest ones in this exercise or in any induction proof exercise, which are the first 3 steps. Now on to p of k plus 1. On the inductive step, which is p of k plus 1, we want to rewrite p of k, but replacing k by k plus 1. And going 1 iteration more for p of k, meaning we're going to have an extra term. So we have 1 plus 2 times half plus 3 half squared plus 4 half cubed plus all the way up to k half to the k minus 1 plus, and here's the extra term, k plus 1 times half to the k plus 1 minus 1, which of course can be rewritten as half to the k. And we need to prove that this is equal to 4 minus k plus 1 plus 2 over 2 to the power of k plus 1 minus 1, which is, again, 2 to the k. So there we have it. Now it's important to remember that we are going to start with the left-hand side of p of k plus 1. We're going to make this substitution over here, somewhere over here. We're going to see it in a minute. And the goal is to get to this. So the goal is to get here. Now let's start with the left-hand side of p of k plus 1. So starting with the left-hand side of p of k plus 1, we have all this, which I'm just going to copy and paste because I can. And knowing that this sum right here can be rewritten as this, given that this is our assumption, we're assuming that this is true. This is part of our induction proof. This assumption right here, we are going to replace all this by 4 minus k plus 2 over 2 to the k minus 1. And we still have, of course, this last term. Now, notice that this half to the k can be rewritten as 1 to the k over 2 to the k. And given that k is a positive integer, 1 to the k is just 1. So we can write it like this. Therefore, we have 4 minus k plus 2 over 2 to the k minus 1 plus k plus 1 over 2 to the k. Now we can put 2 to the k as our common denominator, which means that we're going to have 4 times 2 to the k minus k plus 2 times 2, which is the difference between this denominator and this one. We're missing a factor of 2, so that's why we multiply this by 2 plus our last term, which is k plus 1. So let's see what this simplifies to. We have 4 times 2 to the k minus 2k minus 4 and then plus k plus 1, which can be simplified to minus k minus 3 over 2 to the k, which can also be rewritten as 4 times 2 to the k minus k plus 3 over 2 to the k. And you probably see where this is going. Notice how close we are to our goal. We're only missing a few steps. We can break this into two fractions, 4 to the 2k over 2 to the k minus k plus 3 over 2 to the k. We can simplify these 2 to the k's here, and in order to get something similar to this, which it's of course the same thing, we can rewrite k plus 3 as k plus 1 plus 2, just to make it look exactly as what we have in the right hand side of p of k plus 1. Therefore, we have 4 minus k plus 1 plus 2 over 2 to the k, which is indeed equal to the right hand side of p of k plus 1. And there you go, that's pretty much it. The only thing that we have left to do is to write the conclusion, the same sentence that we use pretty much every time, with just a few tweaks from example to example or from exercise to exercise, but it looks pretty much the same. So given that p of 1 is true and p of k plus 1 is true whenever p of k is true for some positive integer k, then by the principle of mathematical induction, p of n is true for all positive integers. Now there you go. Let's jump to the second exercise now. All right, so in this case, we have an alternating series, 1 squared minus 2 squared plus 3 squared minus 4 squared plus all the way up to -1 to the n minus 1 times n squared. We need to prove that it is equal to this using induction. The same 5 steps are involved, and the first one is to write the propositional function. So we're going to copy what's given by the exercise and state that this is our p of n. Now, given that we're talking about positive integers, the base case to be used is p of 1, given that 1 is the first positive integer. So on the left-hand side, we have the first term in this expansion, meaning this guy right here, 1 squared, which of course is equal to 1. Now, to find the right-hand side, we're going to replace 1 into n, so -1 to the 0, times 1 plus 1 over 2. And this is giving us 1 as well. Therefore, given that the left-hand side is equal to the right-hand side, the base case holds. Now on to p of k, which is the inductive hypothesis. We're going to copy p of n, substituting n by k, and writing for some positive integer k. So there we go. Let's remove these n's over here and replace them by k, and write after that, assume that this is true for some positive integer k. Now, to tackle p of k plus 1, we're going to take the left-hand side of p of k, go one iteration more, and on the right-hand side, we're going to replace the k's by k plus 1. So we're going to have our initial sum, which goes all the way to -1 to the k minus 1 times k squared, go one iteration more, meaning that we're going to have -1 to the k plus 1 minus 1 times k plus 1 squared. And of course, you can simplify this exponent over here by just k. And on the right-hand side, by replacing this k, this one, and this one by k plus 1, we'll have -1 to the k plus 1 minus 1, meaning -1 to the k, times k plus 1 times k plus 1 plus 1, which you can write like this or as k plus 2. So remember that the goal is to get here. We're going to start with the left-hand side of p of k plus 1, and we're going to aim to get to here by substituting our p of k into the left-hand side of p of k plus 1. So starting with the left-hand side of p of k plus 1, we have this following sum, and these terms, we're going to replace them, given that we're assuming that this is true, by this. We'll have -1 to the k minus 1 times k plus 1 divided by 2, plus this -1 to the k times k plus 1 squared. Now we can put 2 as a common denominator, which will give us -1 to the k minus 1 times k plus 1, plus 2 times negative 1 to the k times k plus 1 squared. As you've realized by this point, to answer induction proofs exercises successfully, you need to be 100% comfortable with algebra. Now, given that we can write negative 1 to the k as negative 1 to the k minus 1 times negative 1, we can use this as a common factor, meaning that we're going to have negative 1 to the k minus 1 times, and let's remove these guys which were already used as a common factor, k times k plus 1 plus 2 times this negative 1 over here times k plus 1 squared. So we have the following expression. Now let's expand this even more. We have k squared plus k over here. We also have k squared plus 2k plus 1, which times negative 2, which is right here, gives us k squared plus k minus 2k squared minus 4k minus 2. All that divided by 2. And simplifying this even more, we have negative k squared minus 3k minus 2. Now, the fact that you have your goal already written, which is right here, should give you a lot of hints as what the next step should be. So for example, we can see that we have negative 1 to the k minus 1, and we actually want negative 1 to the k. So it looks like we need to factor out a negative 1 to be included over here. And that's exactly what we're going to do on the next step. But also, do notice that when you convert this into k squared plus 3k plus 2, meaning they all turn positive, that will be the same as k plus 1 times k plus 2. So it's as if you have the mark scheme with you. So times negative 1, let's make those substitutions, negative 1, well, not substitution, but actually rewrite it in a different way. Negative 1 times k squared plus 3k plus 2, all that over 2. And we have our negative 1 to the k over here. And factoring this, we get k plus 1 times k plus 2. Therefore, we got to the right-hand side of p of k plus 1. And that's it. After you write the conclusion, and I'm just going to copy this one because it doesn't change, you are pretty much done. Now let's jump to exercise number 3 now, the last one. All right, so on to exercise number 3, a classic one. We're going to use the principle of mathematical induction to prove the formula for the sum of the first n terms in a geometric sequence. Now, do notice first that we do have n terms. This is ar to the 0, and we go all the way to ar to the n minus 1, which gives us n terms. And we're going to prove that this gives us ar to the n minus 1 over r minus 1, which is the same formula that you see in your formula booklet for topic 1, sequences and series, which is part of topic 1. Now, starting the same way, writing the propositional function. So we're pretty much copying what the exercise has given us. And to tackle the base case, we are going to use p of 1, given that we're talking about positive integers. The first positive integer is, of course, 1. Now, on the left-hand side, we have the first term, which is equal to a. Now, notice that this is equivalent to a to the r, 1 minus 1, which is ar to the 0, which is just a. So you can just grab the first term or think about it that way. Now, onto the right-hand side. On the right-hand side, we're going to replace not a, not r, but n by 1, which gives us r minus 1 both in the numerator and denominator, which we can cancel out and still get our a. Now, given that the left-hand side is equal to the right-hand side, the base case holds. Now, on to p of k. No surprises here. We just take p of n and replace every n by k, which gives us the following hypothesis. Now, we need to state that we're assuming that this is true for some positive integer k. Now on to p of k plus 1. To write p of k plus 1, we're going to take p of k. We're going to add one term to the left-hand side, so go one iteration more. And on the right-hand side, we're going to replace k by k plus 1. So we're going to go all the way to this term plus an extra one, which we get by substituting this k by k plus 1. So we have ar to the k plus 1 minus 1, which of course you can just rewrite as ar to the k. And on the right hand side, we have r to the k plus 1 minus 1 over, and times a, by the way, over r minus 1. Now, how do we work with induction proofs with series? We start with the left-hand side of p of k plus 1, and by using this assumption, we're going to replace it over here and get to the right-hand side of p of k plus 1, hopefully. We will. So you should write, starting from the left-hand side of p of k plus 1, and we start from here, and by replacing p of k into the first k terms, we have a times r to the k minus 1 over r minus 1, and then we also have this a r to the k. Now we can write everything under or over the same denominator, which means r minus 1 in this case, and we have a r to the k minus 1 plus r minus 1 a r to the k. And we can distribute both these and also these products, which gives us a r to the k minus a plus a r to the k plus 1, which is this product right here, minus a r to the k all over r minus 1. Now we can cancel out the a r to the k's, and we can also factor out a from here and from here, giving us r to the k plus 1 minus 1 over r minus 1, which is exactly where we were trying to get, which is the right-hand side of p of k plus 1. Now this was the goal, and we got to the goal. Now, after writing the conclusion, which is the boring part, you're done.